So this is going to be kind of an extension on the last lesson, which was on similar shapes, and we kind of got the different values of similar shapes in their pieces. So if you don't remember, a similar shape is simply two shapes that aren't congruent, so they're not the exact same, but there's a common change by either multiplication or division that brings us from one shape to the other that kind of acts as a bridge. And that change, that multiplier divider, is what we call the scale factor. So the scale factor is kind of the bridge between one shape and the next. Now, if we're not told the scale factor, so if they don't tell us the scale factor, we can get that pretty easy by simply taking two pieces of the shape and making them into a fraction. Taking one piece from one shape, taking a corresponding piece from the other shape, and setting them up as, like I said, a fraction. So for example, let's start here. We'll say scale factor. If I said, what's the scale factor between these two shapes? So what's the bridge? What's the link? Well, they don't tell me, but I could do this one of two ways. I could take, say, the 3 and the 7.5 because they're both corresponding pieces. They're both representing the same part of the shape, which is this this top right line of each shape. So 3 over 7.5 could be my scale factor. That could be used as my scale factor, my bridge between one shape to the next. For every 3 units I have on this shape, I have 7.5 units on this shape, essentially. So if this side here was 6, this side here would be 7.5, that'd be 15. Because I have two sets of 3 over here, if that was 6, I have two sets of 7.5 over here, that'd be 15. Now, I could also have done it from here to here. So I could also do 2, let me do this in a different color. I could also do 2 and 5 because they're also both parts of they're also representing the same parts of the shapes there. So 2 is the apothem over here, 5 is the apothem over here. And if we assume that this is a regular polygon, all the apothems are going to be equal. So we have 2 over 5. These are both the same scale factor. And again, if you don't believe me, we can go ahead and check it. So for example, 3 over 7.5, that's 0.4, and 2 over 5, that's also 0.4. So these fractions are the exact same, they're just two different ways of writing it. So which one you choose is up to you. Or you can even reduce them down both to be, let's say that'd be 2/5 actually. So 3 over 7.5 actually does reduce down to 2/5 when you reduce it, and then 2/5 is obviously already 2/5. So your scale factor should, if you reduce your scale factor, you should always reduce down to the same fraction for each problem. But you don't necessarily have to reduce it if you don't want to, unless it's required in the problem, which isn't usually. But that's what the scale factor is simply one piece from one shape, corresponding piece from the other shape. And yes, you could flip these fractions, and you could make it 7.5 over 3, and then 5 over 2. So it doesn't necessarily have to be the smaller number on top. It just depends on, again, what your preference is. As long as you're consistent, that's the key. So we use the scale factor notion to help us figure out different pieces of similar shapes. We started with linear measurements, which was like perimeter and length and all that. So this was a common one here where, okay, you have these two polygons. If we assume that they're similar, how can we figure out the perimeter? Well, we're going to say, all right, we're going to have my two fractions. And as I just said over here, excuse me, where is it? There we go. These scale factors should always be the same. So scale factor here should always equal scale factor over here. And if I had another piece, I could set that as another scale factor, and that would also be equal. So if this was x and this was y, then this should also equal y over x. And if this here was, let's say this side here was z, and this was w, then I can make another scale factor as w over z. So no matter what scale factor I make, they should all be the same. And for example, if this was k and this was O, then this would be O over K. So all my scale factors, no matter what I take from them, they all should be equal as long as the pieces are corresponding. So Y over X, W over Z, O over K, they should all be equal to all the other scale factors. And that also holds true for perimeter. So this perimeter over this perimeter is going to act as kind of like a scale factor. So what I could do here is say, all right, let me do this in a slightly different color here. If I say 8 over 34, that'd be my first scale factor, 8 over 34. Well, if that's going to be a scale factor, that should also be equal to this perimeter over that perimeter. So that should also be equal to 42 over what I'll call x. I don't know what the perimeter of this shape is, so I'll call that my x there. Because again, the reason this works, the reason that this equality is always going to be true, is because of the fact that the scale factors are always consistent no matter where you take them from. So if I take length to length, that should equal perimeter to perimeter. If I gave you a number here and I said solve for this side, you can do the exact same thing. 8 over 34 is equal to this number over that number. So again, it's a very uh, reoccurring type of problem here. And like usual, we solve these by cross multiplying. So cross multiply, we get 8x over here is equal to 42 times 34 is 1428. And then we divide everything by 8 because that cancels out the 8 over there. And we get x is equal to, divide by 8, 178.5. 178.5. And that would be the perimeter. So that'd be in inches, but that'd be the perimeter of my other shape there, 178.5. Again, scale factors are all consistent no matter what they give you. So if I could pick a random number. Say I called this side 104, and I said solve for y. I'll put inches here. And I said do that problem. Well, you can do that because it's going to be the exact same problem for the most part. You're going to start with your same scale factor, 8 over 34 is equal to, now again, you do have to be careful because you started with this shape and your scale factor. So you always have to start with that shape every time you make your scale factor, every time you make a complement or a fraction you want to solve with the scale factor. So this would be y over 104, and then you'd cross multiply and solve that one through just like you did over here. So again, consistency is the key. Once you get a scale factor that you know are right, once you got the corresponding pieces, you got the fraction set up, I would even label it small over big. That way, whenever I do a problem, I can always go back and label it and see that it matches up with my scale factor. Then we kind of took it a step up there when we used it to solve for the area. So the reason that the area was a slightly different problem, a slightly more step up of a issue, was that area is in square units, whereas all the other units in the shape are in linear units, or single units. Here we have 12 meters, 6 meters, 18 meters, but the area is in meters squared, not just meters. So what we do to start these is we start the same way. We make a scale factor base, which means we take two numbers that we know are corresponding and we put them as a scale factor. So I have a few options here. I can use either 12 or 6. But here I only have the 18. So whatever I pick over here has to correspond with the 18. So for example, if I picked the 6, I'd be in trouble because 6 is kind of slanted length right here, which means it corresponds to this one over here, which I don't know. So I can't use 6, otherwise I have too many variables. For example, just as an aside here, let's say I did choose 6. And let's say I call this side, I don't know, y. Well, it'd be 6 over y is equal to 63 over x. We'll call my area x. Well, I can't solve for this now because I have two variables in a problem, and I can't solve when there's two variables in a problem. So that's how I know that 6 isn't going to work, because I don't know the corresponding piece to 6. I have too many variables in that case, and I can't make my answer work. Actually, I could leave that x there because we'll just call that x anyway. So instead, I'm going to choose the 12 because then I'm going to choose top side to top side. So 12 to 18, top to top, and then area to area. Now, before I cross multiply, what I said you had to do is you have to square this fraction, because what happens here, let me actually add something to that first, is that this is 12 meters, this is 18 meters, this is 63 meters squared. So there's a conflict here. I have meters compared to meters squared. I can't have that. So I'm going to square this fraction, because that will square the numbers, but when you square the numbers, you also get to square the units. So that would change this into 144 meters squared over whatever 18 squared is. So 18 squared would give me 324 meters squared. And then now I have an agreement with all my units. Everything is nice and agreeing. And so now I can go ahead and cross multiply my values. So 63 times 324 gives me 2041.2. So 2041.2. And then 144 here. And then I divide by 144. I divide by 144. And I get, divide 144, 141.75. So 141.75 meters squared would be my area for the big shape. Okay. Again, I went small to big, so I went small to big in my second fraction. Again, consistency is the key. But when you have the area, just remember to square your non-area fraction first. So this was a linear fraction because it dealt with the lengths. This was an area fraction because it dealt with the area. I had to square my linear fraction. That way it agreed with my area fraction, or at least agreed in the units that we're using, and then I could proceed from the problem. You can also go backwards here. So in this case here, we have both areas, and I want to find the missing piece over here. And I have a corresponding piece here. So once again, I can start this off the same way. I'll label this x. I have top left line, top left line. So set them as the fraction. Top left is equal to, and then keep my area fraction consistent. Small area, big area, because I went small to big over here. So 20 yards. Woo, I hate when that happens. And it never gets rid of the number either. I have to go in and manually delete it. That's annoying, but okay, we'll continue. So 20 yards squared and 46 yards squared. Boom, boom, done. All right. So once again, we have a disagreement. I have yards over here. I have yards squared over here. I don't like that to happen. So I'm going to have to square this fraction. That way, all my stuff is nice and agreeable. Now, you might be noticing here that we're going to get an x squared afterwards, and that is absolutely 100% correct, which is fine because we know how to deal with x squareds because we're high schooler students, or at least close to there. So we have 100 yards squared over x squared is equal to 20 yards squared. I can't write for some reason, over 46 yards squared. There we go. And then now we can go ahead and do my normal cross multiplying business here. Just remember that this is an x squared now, not an x. So you have to make sure you're careful with how you write your stuff. So 20x squared is equal to 4,600 yards squared, but I'll leave the label off for now just to make it easier to see. And so then we divide by 20, and we get x squared is equal to 230. And then to get rid of the square, we then square root both sides, and we get x is equal to whatever the square root of 230 is, which is 15.165. So 15.166, because after the 5 is a 7, so the 7 rounds the 5 up to a 6. And that'd be yards. Because again, this is a linear measurement, so it should be in yards. We could also figure that out, by the way. There's another way I told you could do this, but it works better with this problem up here, actually. So let me actually talk about it up here, and then I'll tell you how we could have done it down here. So what you could do here is this scale factor is, again, what you multiply or divide by to go from one shape to another. So for example, let's take the scale factor, 12 over 18, and let's make it into a decimal. So 12 over 18 is 0.6 repeating. So I'll do 0.6 repeating. So what that means is that, since this is a small number, if I take 12 and divide it by this, so if I take 12 and divide it by 0.6 repeating, I should get 18. And if I take 18 and multiply it by 0.6 repeating, I should get 12, which again does indeed happen. So 12 divided by 0.666, we'll just enter a bunch of sixes in here, and I get 18. And then if I go backwards and I take 18 times that, I get 12. Again, that's what the scale factor does. It tells you what the bridge is. Well, you could do that for area as well. Area follows that same rule, except that, once again, it's going to be a squared scale factor. So 12 divided by this gives me 18. That means 63 divided by 0.6 repeating squared will give me that area, which, again, if we do it right, it should give me this number here. And it does indeed, if I prove this to you here. Just enter a bunch of sixes, and it does indeed give me that number. Okay? This is how you trick the calculator doing repeating, is you just enter it a bunch of times, and the calculator will eventually get the idea. So you could devolve your scale factor down to a single decimal and then just use the multiplying trick here or the dividing trick here, depending on which way you go, to go from one to the other. Just check to make sure you're doing it the right way. Like, let's say, for instance, you were doing this too quickly and you thought it was 12 times 0.6 gives you 18. You can pretty much see 12 times 0.6 repeating. that doesn't give me 18, that gives me 8. So then you would think to yourself, okay, well, multiplication doesn't work this way. Let me try division with 0.6 repeating, and then that one would work, and then you know which way is multiplying, which way is dividing. So if you're confused about whether to divide or multiply, just test it out for one of them, see if it works for the two sides you know. If it doesn't work, then you know it's the opposite way. The same holds true here. You just be a little bit fancier about it. So our scale factor was this right here, right? 20 over 46. So 20 over 46 gives me 0.4348, we'll say. So 20 over 46 gives me 0.4348. Now that's not my scale factor though, because it's made with the areas. So my actual scale factor is not this, but the square root of that. Because remember, this was made for areas. So if I want to go back to the linear measurements, I have to square root it to bring it back down from being squared. And then that would be the number I would use. So square root of that number would give me 0.6594. So 0.6594. And then this would be my multiplier or divider. So I could take that and then I say 10 divided by that, and that should get me pretty close to 15.16 repeating. Right. So not 16 repeating, but 1657, and the 7 rounds the 5 up to a 6, and then we get the same thing we did here. So again, you can use that trick if you're the type of person that likes to do that. Or again, you can always just go back to the tried and true way of set your fraction, cross multiply, and then square if you have the area involved. Okay? This is just a little shortcut if you choose to practice it. So what this is leading up to is this last type of problem, which we have are called scale drawings. This is used by craftsmen, artists, architects, anybody that deals with building stuff. They usually do a scale model of stuff first, and then they find out, okay, how's this going to look, and then they go ahead and do the actual thing. So we're going to look at some types of problems that go into that sort of skill set. So let's just get right into it here. An interior decorator is making a room layout. In the layout, every 4 centimeters represents 5 inches. Given the diagram below, how long would the actual couch be in inches? So we want to figure out how long the actual couch is, not how long the drawing is. Now, you might be thinking here, well, I don't have a scale factor, because usually when you do these, you have two shapes, right? You have one shape that's usually smaller than the other. You have two sides. You can make a fraction, and you go about your day. Problem here is that you don't. However, they actually tell you your scale factor. So these word problems can actually end up being easier because in the wording, they actually give you your scale factor. And the way they do that is they tell you what the drawing represents to the actual. So it says here, in the layout, every 4 centimeters represents 5 inches. This is your scale factor. Now, yes, the labeling doesn't agree, but you'll see why that doesn't matter in a second here. So my scale factor is actually gotten from this phrase, every 4 is equal to 5. So for every 4 centimeters, that's equal to 5 inches. So every time I have 4 centimeters in the drawing, I have 5 inches that the actual couch is going to be. So if I want to set this up, now I can set up like a normal scale factor problem. 4 centimeters over 5 inches, and there's a reason I'm keeping the labels here, and you'll see why. So now your question is, okay, this 60, does that belong on top or bottom? Because again, what's happening here is I have an imaginary or real couch here. So this is the actual couch, so the real couch. And I want to know how long is it. So if I did 4 centimeters to 5 inches and 60 is a centimeter number, well, that means that 60 is going to go on top because that's where my centimeter number went on the first time. Centimeters on top, centimeters on top. Inches on bottom, inches on bottom. If you want to put inches here, that's fine too. So this would be my scale factor setup. Again, everything agrees. Centimeters to inch, drawing to actual, 4 centimeter drawing, 5 inches actual. 60 centimeter drawing, how many inches actual? That's what I'm basically trying to figure out here. So now you would cross multiply, and once again, some of you are probably saying, well, your units still don't agree. Don't your units all have to agree? Not necessarily if they cancel out. And here's what I mean by that. Let me go ahead and multiply here. So multiply. 5 times 60 is 300. We'll say 300 centimeter slash inches because we're kind of multiplying these labels together. So we'll say centimeter inches is equal to 4 times x. So that'd be 4 centimeters times x inches. So what I'm going to do now is divide everything by 4 centimeters, right? Because that's how I get rid of 4 times something as I divide it. And again, I'm keeping the labels in here to show you something. So divide by that. So 4 centimeters and 4 centimeters, that goes away. Over here, 300 divided by 4. Let's just do that real quick. 300 divided by 4 is 75. Now, this would be 75 inches, and some of you might be wondering, well, okay, why is it back to inches now rather than having to agree on the units and all that? Well, that's because the 300 over 4 gives me 75. Centimeters divided by centimeters, that label cancels out, actually. It's just like a number. Here, 4 and 4 canceled, and centimeters canceled. Here, 304 quote-unquote canceled and made 75. They combined, but we can call it canceling if you really want to. And centimeters just cancel out. And so all I'm left with is inches. So this goes from being centimeter inches to just inches. Something called dimensional analysis if you want to look it up. And that's going to be equal to x inches. So now I know that x is equal to 75. So the actual count would be 75 inches total if it was 60 centimeters in the drawing. So that's why here, yes, the labeling doesn't agree, but they're arranged in such a way that when I cross multiply, the labels I want to get rid of cancel and the labels I want to keep stay. So by setting up like this, when I cross multiply, my centimeters will cancel and my inches will stay in the problem. Now, do you have to keep writing your labels every time you do a problem? No. The only reason I wrote the labels here was to show you that that's what happens. That unlike the area problems, which is a completely different problem, so don't try and mix these two, but unlike the area problems where you had to get like everything in square units and in the same square units, for the scale drawing problems, you don't have to because of this fact that as long as you set up as drawing over actual, as long as you keep that setup, the labels you want to get rid of will get rid of naturally, and labels you want to keep will stay in there naturally. Now, speaking of areas, you can do this for areas as well. But again, you just have to find the area yourself sometimes. So like here we have a weird looking shape here, and it says a toy designer is modeling a toy after a certain statue. So evidently this is the picture of a statue somewhere. And the shape of the measurements of the statue are given below. So this is actually the actual statue. So this is the real statue. What would the area of the toy model be if every 3 inches on the model represents 2 feet on the statue? So once again, you have to start by knowing what your scale factor is, and in these types of problems, they will tell you it. 3 inches on the model, 2 feet on the actual. So let's go ahead and write that down. 3 inches on the model, I'll put model here, and 2 feet on the actual. We'll put actual. Okay? So 3 inches model, 2 feet actual. Now if I want the area, I first need to figure out the area of my statue. That way I know how much area to give to my model. So let's figure out the area of this. And this is a composite figure. It's made up of 2 different shapes. You could cut this up into maybe like a triangle, a rectangle, and then another rectangle on bottom. But the way I see it is I see it as top trapezoid, bottom rectangle. That way I only have 2 shapes to deal with. And the less shapes I have, the happier I am. So we'll do the rectangle first because rectangles are usually easier. So I have that this is 8 feet. I need to figure out how big this section is right here, because that will give me my base times my height. Well, I know the entire thing is 16. I know that from here to here, that's 4 feet, because that's the height right there. So from there to there is 4 feet. So this would also be 16. Come on. It'd be 16 minus 4. So 16 everything minus the 4 feet up here would give me 12 feet. So this rectangle would be 8 times 12. Let's see, that would give me 96 feet squared, because it is area, so it's square feet. And yes, okay, I'm right. I knew I was. So 96 feet squared. And on the top here, we have a trapezoid. So we need the base 1 plus base 2 divided by 2 times our height. So base 1 is 10. Base 2 is 5 feet plus 8 feet because I want the entire base 2, so that's 13 feet. Times my height, which is 4, all over a nice even 2. So this, let's see here, that'd be 23 times 4 divided by 2, which would be 46, I think. I'm always second guessing myself nowadays. 46, yeah, I'm good. So 46 feet squared. So the area of everything, if we add these two together here, 46 plus 96 would give me 142. So 142 feet squared. So this statue has an area of 142 square feet. So if I want to find the area of my model, right? I want to find how much area my model toy should have to compare to the statue. Well, I'm going to set up like I did the last one. Set up with my scale factor. 3 inches over 2 feet is equal to, now I have to be careful here. This was model over actual. So this one also has to be model over actual. I have to keep that same consistency. So I don't know the area of my model. So that's x. I do know the area of the actual statue now, and that's going to be 142 feet squared. Now, once again, we have a disagreement here because I have feet squared here, but I only have feet here. If you look at the past one, notice how these maybe didn't agree this way, but they agreed this way. Inches, inches. Centimeters, centimeters. So they didn't agree top and bottom like they usually do, but they did agree across from each other. I should have that in this case as well. So if this isn't square feet, then I have an issue. But like we said before, if we have an area problem with similarity, then we square the non-area fraction. We can take care of that unit issue by simply squaring our non-area fraction. So 9 inches squared over 4 feet squared is equal to x over 142 feet squared. And now I have an agreement here to here. And because this is my model is going to be measured in inches. So I do want x to be in inches squared. So whatever this label is here, inches squared, that should be the label that is going to go with my x, and it is, because I want the area of the model. The model is obviously measured in inches, so therefore I want the area in square inches. So that's good. Again, if the dimensional analysis unit thing is confusing you, just follow the rule of if you have an area in the similarity problem, you should square the fraction that doesn't have the areas. So let me even type that out here because we all know how good my handwriting is. So the shortcut thinking about this is if you have an area in a similarity, there we go. If you have an area in a similarity problem, then square the fraction that does not have the area values. So that's why I squared this fraction here, because these were not area values. These were linear values. So I squared the not area values, and then now I can go ahead and cross multiply to my heart's content. So multiply, multiply. So 142 times 9 would give me a rather large 1278. So 1278 is equal to 4x. And then divide by 4, divide by 4. I'm not going to bother writing the labels out again just because I've already gone through that. And again, I don't feel like muddling that up here. So it'd be 319.5. So 319.5 inches squared is how much area my toy model should have. So this is, like I said, these problems are actually, in the end, probably a little bit easier than the other ones we did in the previous video. It was because they tell you the scale factor. You don't have to go looking for it like you had to do, say, on this one. This one, you had to kind of look and actually make your scale factor yourself by taking the pieces individually and setting them equal to each other. Whereas in this one, they just flat out tell you 4 centimeters, 5 inches, 3 inches, 2 feet. So as long as you kind of understand what those numbers are representing, model to actual, or model to statue in this case, then it's actually a little bit easier in the end. And then we can have it kind of muddled up a little bit. So sometimes they give you a picture that's already kind of pre-labeled, and they just want a specific piece of it. So let's just kind of, again, look at how this problem plays out here. So diagram below maps the various rooms for the floor of a kitchen house, or sorry, for the floor of a house. The drawing 2 inches represents 3 feet. So again, red flag there. Okay, in the drawing, whenever you use the word represents, that means that that's the middle of your scale factor. So 2 inches represents 3 feet. So let me go ahead and write that down here. 2 inches represents 3 feet. And it says 2 inches in the drawing. So I'll put drawing over actual. 2 inches in the drawing, 3 feet in the actual. What is the area of the kitchen? Well, again, this is a composite figure. So if I want just the kitchen area, I'm going to do some subtraction because I can't figure out that rectangle by itself. So let's figure out how big this side here is first. So the entire thing is 21 inches. We have that from here to here, that's 5 inches. And we know that from here to here is 2 inches. So we need to figure out how much is left for this side right here. How would be the best way of doing that? Well, let's figure out some piece that we don't like, this piece right here for the pig room. If this thing's 21, these two together, we'll put these two together. So from here, let me draw that a little differently here. And I might need to give you one extra value in here now that I'm looking at this. So from here to here, we know that that's 19 inches. Oh, actually, why are we looking up top here? Some of you might be screaming at me right now. The bottom's going to be much easier to figure this out, isn't it? So if this is 21 inches on top, that means down here, that's also 21 inches. And this is already better labeled for us. So up top here we have 2 inches, which means down below here we have 2 inches. And we can figure out this way. So 2 inches plus 15 inches. So these two together are 17 inches. And if I need 21 for the total length, that means this one right here has to be whatever's left over. So 21 inches minus the 17 that I already have means I'm going to need 4 inches left, right? 21 minus 17 is 4. Right. So this top part here is 4 inches for the kitchen. Then I need this part right here. So again, don't get pigeonholed like I did in trying to look at one side of your shape all the time. Look at the bottom here, and the bottom's actually better labeled for this than the top was. We could probably finagle our way through it if we just use the top side, but again, why not use the information you have on bottom to help you out, right? So now we need to figure out this side over here. And we know the entire thing is 8. It says that right here, this 5 belongs to this right here. So this side right here is 5 inches. The entire thing is 8 inches, which means that this side left right here has to be 3 inches. Because 5 and another 3 give you the full length of 8. So let's go ahead and see what I can do here. That means that this kitchen here, let me work on I write this. We'll just put it right here. So the kitchen is equal to length times width, or base times height. So it'll be 12 inches squared. So that's how big the kitchen is. So I want to figure out, well, that's how big the kitchen is in the drawing. I want to figure out how big the kitchen is in the actual house. So let's go ahead and set up my scale factors now. So 2 inches over 3 feet, that's what I started with, is equal to 12 square inches over x square feet, hopefully. And once again, the red flag here is I have area numbers. I need to square the fraction that doesn't have the area numbers in it. So here would be 4 square inches. This would be 9 square feet, which is good because I want square feet as part of my x. I want my x number, which is the actual area of the kitchen, to be in square feet because that's how I'm measuring my actual kitchen or my actual home is in square footage. And then now we go through our tried and true method of cross multiplying our lovely friends here. So this would be 4x. I don't recommend cross multiplying your actual friends, otherwise they might not be your friends anymore. 9 times 12, unless they like math, is 108. Divide by 4. X equals, divide by 4, 27. And this would be in square feet, or square footage as the lingo goes. So the actual kitchen will be 27 feet squared when it's done if they draw or if they build it according to this model here. So again, these problems are no different than what we did before, except that they're basically the word problem versions. They give you everything in the wording of the problem rather than you having to hunt for it in the pictures. And again, if you know how to work them, they can be a lot more easier than they might sound at first. But just remember, if you have an area, square the fraction without the areas. If you don't have the area, if I asked you like what the perimeter was or something like that, then there's no reason to find or no reason to square anything. Just find the perimeter of the drawing, apply your scale factor to get the perimeter of the actual shape. So I would do 2 over 3 is equal to, I'd find the perimeter of this shape here, and say that over x, and then cross multiply, and I get the perimeter of my actual room or floor or whatever. So that's it for this video. Hope it helped you out. Hope you're staying well. Please let me know if there's any questions or if you just want to chat or vent. And I will see you next time, metaphorically speaking.